opening of L-type calcium channels.
So opening of L-type calcium channels.
Resulting in increased permeability to, resulting in increased calcium influx.
Influx.
As calcium comes in, being that it's positive, it makes the voltage more and more positive. Depolarization.
Depolarization.
What stops depolarization here? Why doesn't it keep going? The L-type calcium channels close. And as they're closing, what's actually opening?
Calcium.
Voltage-gated potassium channels. Resulting in an increased permeability to potassium and a decreased permeability to calcium, right? No rectifier names for the autorhythmic cell, just voltage-gated potassium. All right, so we have an opening of voltage-gated potassium, increased permeability to potassium, resulting in increased efflux of potassium.
Is that at like plus 20?
Yeah. And then as we lose the positive charge, as potassium leaves, the interior goes to the exterior. The interior of the membrane gets more and more negative. So that's the rapid repolarization phase.
Rapid repol phase.
And this is rapid dipole.
Rapid dipole.
And the only reason I put the rapid before is because this is dipole as well. And I don't want you to confuse the two different types of depolarization. So this one's rapid dipole, this one's drift. It's a very slow dipole. So what's happening at the bottom here? Voltage-gated potassium channels are closing, and at the same time, funny channels are open.
Funny channels.
So what's happening to permeability to potassium as we close those potassium channels? And then as the funny channels open, sodium permeability goes up. Now, even though potassium can go through the funny channels, what we're closing are way more abundant than what we're opening. Right? So we had all those voltage-gated potassium channels that were open that dramatically increased potassium permeability. We're closing them. That's why potassium permeability is going down, even though we're opening the funny channels. What's more important, though, isn't the number of channels that are open for sodium or potassium. It's the electrochemical gradients that they have at this very negative membrane potential. We can't call it rest because there is no rest, right? Autorhythmic cells do not have a resting membrane potential. But when we're down here near minus 70, even though we do have channels still open for potassium, the funny, the leak, why doesn't very much potassium leave at this point? We're very close to its equilibrium potential. So the EC gradient is weak. And why does so much sodium come in? Very far from its equilibrium potential, very, very strong electrochemical gradient. Sodium influx dominates potassium efflux. That results in drift. As we come down, potassium efflux is still greater than sodium influx. We haven't opened enough funny, haven't closed enough potassium channels quite yet. That transition point, they're equal for a brief moment, sodium influx, potassium efflux, and then as soon as we start depolarizing, that must mean sodium influx is dominating. Sodium's coming in through funny channels. Funny channels now start to close. What's going to open to keep this going to threshold? T-type calcium open. Calcium influx continues the depolarization. And T-type calcium start closing, L-type open, rapid dipole. They close, potassium open, rapid repole. What happens to the repolarization phase when we turn the dial up on parasympathetic output to these autorhythmic cells? Does the repole become longer or shorter? So if it's longer, we're going down further, right? Even more negative. What's that called? Hyperpolarization. It's going to lead to hyperpolarization. Well, what is it that the parasympathetic nervous system is doing to create this hyperpolarization? inhibiting funny and T-type, and at the same time, right, enhancing the opening of the potassium channels. So what we needed to turn this around was less potassium efflux, closing the potassium channels, more sodium influx, opening the funny. We're not opening as many funny. We're keeping more of the potassium channels open, so it doesn't turn around quite as quickly. It's going to take a little longer before enough funny channels have opened, enough potassium have closed to turn it around. And then when we turn it around and start drifting, how is that slope going to be different? So you would describe that as a flatter slope, right? It's not as steep, it's more flat. Or you could just describe it in terms of time, a longer drift. It results in a flatter slope. That just describes the line on the graph. Or you could say it causes a longer drift. Lengthens the drift potential. So now we have to wait a little bit before we reach threshold. So two things are making it take longer to reach threshold. One, we're starting further from threshold. And two, when we drift, it's a much slower drift. What is the sympathetic nervous system doing to this autorhythmic cell action potential? Reducing repull, turning it around sooner, and then the drift becomes fast, steeper slope. Shorter, faster drift, steeper slope. How? What's that?
Longer, slower, or?
Yes, longer, slower, then faster, shorter. Yeah. How is sympathetic doing this? What's the mechanism? So epi, norepi stimulate which receptors? Beta 1 increases cyclic AMP, protein kinase A, leads to phosphorylation of funny and
T-type.
T-type calcium. Funny and T-type. Which are the two channels that are responsible for what phase? The drift. So when the funny start opening, more open, we turn it around sooner. And as they close, more T open. So not only is the early drift steeper or faster, so is the late, the whole thing. So we didn't have to do anything to the potassium channels. It was enough to just increase the opening of funny to turn it around sooner and get that steeper slope.